Hello everyone, once again we will continue with chapter 6 section 5. In this section we are going to look into the isentropic processes. Okay, so we have defined the isentropic process, that's basically constant entropy process, but from the entropy balance, if a process is both adiabatic and internally reversible, it means it is also isentropic, right? So we treat these isentropic processes as ideal work processes. Consider energy balance for the control mass for work processes. That's going to be delta U is equal to Q minus W, right? And typically, delta U is equal to minus W because it is adiabatic. So this work process is referred to, okay, since this control mass, it doesn't mean the same thing, but it is typically, okay, adiabatic process. So the only part is we are interested in the work. This is what it means by the work process. Okay. So this work is in magnitude much greater than the heat. Okay, so that's why we neglect the heat transfer. So it means it is adiabatic. So that's what I meant. So usually we approximate ideal work processes as adiabatic. And since it is ideal, right? Are internally reversible. So when you combine these, as I did before, okay, so it is adiabatic plus internally reversible, then it means from the entropy balance, it is isentropic process. So that's why we treat ideal work processes. So work process means Q is 0, it's ideal. And ideal means it is internally reversible. So eventually it becomes like an isentropic process. And how we found the isentropic process is as such. Okay? So in the control mass, okay, so we are given a control mass and it is adiabatic and it is internally reversible. It is an ideal system. So as you can see, it is an isentropic process. Let me rewrite this one. And typically you know the initial condition, but you don't know the final condition. Okay, if you remember the cycle example that I did in the previous videos, that's what we had. Let's say you are given the T1 and V1, okay, and you know V2 that is given, okay, and you know that it is isentropic process. So the question is, what is T2, for instance? How do you find T2? Okay, so what I'm trying to say is, you know, isentropic does not belong here, it belongs to here. You know the inlet condition, you can fix the first state. You know what kind of a process you have. In this case, you have the isentropic process, and you only know one property for the final state. Okay, so how can you fix the final state? That's kind of the question. This is just an example. Temperature is just an example. For saturated phases, if you are using saturation tables, this is straightforward actually. You have state 1, you have state 2, temperature, specific volume, and S. Let's make a state table. You are given temperature and volume at state 2, right? So what you can find from the first state using the tables is S1, right? because this S1 is S at T1 and V1. So from the tables, you can find this S1. And then since it is isentropic process, S2 is equal to S1. Okay, now you know specific volume and S. So these are two independent intensity properties. Using these two, okay, then you can find the temperature. Okay? So then you can find T2 as a function of V2 and S2. So since this process is S, okay, since this process is isentropic, to denote that the isentropic state for the final, we typically put an S for the exit state. We do 2S rather than 2. This indicates that, okay, S2S is equal to S1. Okay, so this S, subscript S, denotes that the process is isentropic from 1 to 2. Okay, so the 2S is the isentropic exit state. So using this one, we will, using this notation, you are indicating that process is isentropic. We will use this a lot when we are analyzing the cycles in chapters 8 through 10. Okay? So for the saturation phases, use the tables. Okay, so this comes from the tables. This blue one is also from the table, the related table. This also includes the not only saturated phases, but it also includes the compressed liquid and compressed liquid through superheated vapor. Okay, so from compressed liquid through superheated vapor, you can use this kind of a relation because you have tables or you have some relations that you can find the entropy from the tables. Now, more interestingly, if you have an ideal gas, with variable specific heat. With variable specific heat means CV and CP changes with temperature. Okay? In that case, we have these isentropic relations. Okay, for isentropic process of an ideal gas, we have these relations. The pressure ratio P2S over P1 is equal to PR2S over PR1. What is PR? It is just a parameter. Okay, I will tell you that one in a minute. And similarly, the volume ratio, specific volume ratio, is equal to VR ratio. Okay, and this PR and VR are tabulated in table A22 for air as an ideal gas, right? That's the air table. So let me show you that table. So this is table A22. As you can see, as a function of temperature over here, we have the specific enthalpy that is tabulated, specific internal energy that is tabulated, and S naught. This is not entropy. This is just the temperature dependence part of the entropy. Okay? Remember our discussion. And here we have two additional columns, as you can see, and it says when delta S is equal to 0, and it has a footnote. Delta S is equal to 0. It means it's an isentropic process. Okay? So for the isentropic process, we have PR and VR that are tabulated here. All right? So, for instance, if you know T1 and V1 and V2, what you do is, that was the example, remember that one. Okay? what you are going to do is VR2s is equal to V2s or V2 over V1 times VR1, right? And this comes from the table that you know, right? These are given, that's in the problem. So from here you calculate this VR2s using this relation. And then, since you know VR2s, okay, this corresponds to a particular temperature in that table. Okay, so let me show you the table once again. As you can see, for each temperature, there is a specific VR value. So since you know T1, okay, you can check the VR from this table. That's going to be VR1. And then calculate VR2 and go back to this table again, if it is air, obviously. Go back to this table and check the VR value. There is a corresponding temperature for that VR. Then you know T2. Okay? That's kind of the idea. So when I say table over here, this table means VR at T1. Okay? And here, once you know this value, okay, there is VR2s is nothing but VR at T2s. Then from here, you can find T2s, which is the final temperature, which is what is asked. Okay? So this is the case if you have the variable specific heat, you need to use the tables. And we only have VR and PR for air. For the other gases, we don't have them. Okay, so you don't have any option for those. If you have constant specific heat, this was the variable specific heat. If you have constant specific heat for ideal gas, with constant specific heat. In this case, Cp and Cv are constant, and we had this relation, if you notice, from the previous video. Cv ln T2 over T1 plus R ln V2 over V1. This is for an ideal gas with constant specific heat. Cv is constant. It doesn't vary with temperature. So, since this is isentropic process, this part is equal to 0. Delta S is equal to 0. Right? So, from here, we can write this as ln T2S over T1 is equal to minus R over Cv ln V2 over V1. And R over Cv, R is, if you remember, it is Cp minus Cv for an ideal gas over Cv. So that's basically Cp over Cv minus 1. Cp over Cv is nothing but K. So this is K minus 1. Right? So that becomes T2S over T1 is equal to V2 over V1 to the power 1 minus K. Or we typically say write this as V1 over V2 to the power K minus 1. So this comes from this relation. I use this relation because I know the volumes, specific volumes, right? So this is going to be V2S actually, to denote that it's isentropic exit state. So here I know the volumes. If Cp is constant, we know K. T1 is known, so we can solve for T2S from this relation, which was the objective. Or from the other delta S relation, which was Cp ln T2 over T1 minus R ln T2 over P1. Okay, if you work it around, if it is 0, you will find T2S over T1 is equal to P2 over P1 to the power K minus 1 over K. Okay? So, sorry. If you combine these, T2S over T1 is equal to P2 over P1 to the power K minus 1 over K. That's equal to V1 over V2 to the power K minus 1. So this relation is important. If you notice, this is nothing but what we'd write in chapter 2 actually for an ideal gas. Actually, chapter 3 after we define ideal gases, sorry. But K was equal to N. And it was for a polytropic process of an ideal gas, okay? So this is applicable under 3 conditions. First of all, you have to have an ideal gas. You have to have constant specific heat, second of all. And third of all, you have to have isentropic process. All these 3 must be met in order to find this or use these relations. It has to be an ideal gas, you have to have constant specific heat, and you have to have isentropic process so that these relations are applicable. And as you notice, isentropic process of an ideal gas with constant specific heat is nothing but polytropic process, as you can see, with the polytropic process exponent is equal to K, which is Cp over Cv. Okay, so that's kind of the thing. So you have seen this relation before, but instead of K there was N, but this is what we have. Okay. Again, I have to repeat, I have to emphasize this one. This relation is applicable for an ideal gas with constant specific heat, and you have to have an isentropic process. Otherwise, do not use this one. I emphasize this one because it's a common mistake. Okay? So when I say polytropic process, P2 V2 to the power K is equal to P1 V1 to the power K. Okay? Where K is Cp over Cv, and it's constant. All right. So we have covered all these things for controlled mass systems. In the next section, in the next video, we will cover these for the control volume system. Okay. So let me know if you have any questions. Take care. Bye.